We're going to get into some problems today that also involve counting. And so this multiplication principle, you see it in this first section, but it's just going to be a part of your toolbox now. So if you find yourself in these problems where you have to make 2 or 3 choices, then just draw the lines underneath. You know, I got to make this choice, and then I've got to make this choice. I'll figure out the number of ways to count up the first choice I have to make, and then I'll figure out the number of ways I have to do the second choice. But some of those choices that you come up with will be permutations and combinations. They'll be complicated in themselves. And so we're going to look at counting, permutations, and combinations. These problems come up a lot in probability or in odds of cards, for example. You know, if you play cards and you have, like, say, a 7-card hand, and you're wondering, you know, what are my chances of getting 2 7s? You can actually calculate that, or you'll be able to calculate that after this section. And in order to do it, you have to be able to work with permutations and combinations. And so that's where we're going. And these 2 mathematical topics use factorials. And so we start off this section looking at or reminding you how to work with factorials. So here it is. The 0 factorial, it doesn't have a whole lot of meaning. And so we're just going to let that be the definition. And then if you have an example like 4 factorial, you start with the 4, and then you multiply it all the way down to 1. So you multiply it by all the whole numbers, beginning with 4, all the way down. 4 times 3 times 2 times 1, and you get 24. If you had something like 7 factorial, then you'd have to start at 7. But again, you multiply by each and every whole number, beginning at 7, all the way down to, now you don't want to go to 0, because as soon as you multiply by 0, then everything is 0, and that's not a very interesting function. You stop at 1. And, you know, I have no idea what this is, but it's a huge number. 24 times 5, 720, 49, 50, 40, something like that. And just to show you that the calculator has a nice function for you. It's in the math menu here. And so all of the functions that you're going to see today are in the math menu. And when you press this math key, I'll write the keystrokes over here, you get this menu, and everything that we do today will be over here in this probability menu. So you'll want to scroll over there, and there are really 3 functions in this menu that we're going to use. You can see the factorial right there in number 4, the exclamation point. And then you have the NPR, P stands for permutation, and NCR. NCR stands for combination, permutations and combinations. But for this one, we want option number 4, which is the exclamation point. Okay, so if you wanted to do 7 factorial, you'd type the 7 first, and then go to the math menu, and then over to the probability menu, and then select option number 4, and then hit enter. And it'll give you that number pretty quickly. Another thing that you'll be able to do is that you're going to have factorials in the numerator and in the denominator of fractions. And so we're going to use this property of canceling fractions, canceling factors in the numerator and denominator quite a lot. And so here are some sample problems. So they get you working with factorials, and they get you working with cancellation. So for example, 3 times 2 is 6. So if I cancel out all of those, that's a factor of 6. And I can cancel a factor of 6 out of 12, leaving the remaining factor of 2. And then 2 times 11 times 10. So do these problems by canceling. This is part of the kind of the review section of the exercises. But you have 110 plus 2, that's 220. You'll be doing a lot of canceling like this, things that look like this. So look for numbers that multiply together. So for example, 5 times 2 is 10, and that'll cancel out the 10. 4 would cancel out the 8, leaving a factor of 2. 3 would cancel out the 6, leaving a factor of 2. And then you just multiply all the numbers that remain. I think in all of these problems, what you're going to see is that all of the numbers in the denominator will cancel. And so you'll be left with the numbers that don't cancel in the numerator. And you'll need to multiply them all together. All right, so everything in the denominator other than 1 cancels. 7 times 9, 63 times 4, 252. Now, in number 5, because of this pattern that you observe, this one in the denominator starts at 98 and goes all the way down to 1. That's called 98 factorial. In the top, you have 100 going all the way down to 1. So that's 100 factorial. But 100 factorial contains almost all of the same factors as 98 factorial. What you can do is you can cancel all these 98 times 97 times 96, but you can do the same thing up here. Cancel all the factors from 98 down to 1. 1 for 1. Cancel the 98 on top and bottom. Cancel the 97 on top and bottom. And even though you don't see a 97 here, you know it's there because of the pattern. So the only two numbers remaining are the 99 times 100, and that one you can do in your head. And so how many different ways? 900 or 9,900. All right, go ahead and write the answer to number 6 via canceling, no calculators, in the chat. Number 6. What's going to cancel? What's going to remain? Joe is first. And then Giannis and Marcio and Brooke. Yeah, so you know what's coming after this 9. It's then 8, and then 7, and then 6, and 5, and then 4, 3, 2, 1. And all of those are going to match the numbers in the bottom. And so you have to multiply those 3 numbers together. 990. I'll do the others and put them in the chat. No, I'll put them on the notes, not in the chat. All right, so in some of these, you're asked to evaluate these, just evaluate the expression. So change it to something that has the exclamation point, the factorial, to something that doesn't. So 10 plus, or 7 plus 3 is 10. And remember, order of operations apply here. So you got to do the calculations inside parentheses first. You wouldn't want to take 7 factorial and then add that to 3 factorial because you'd get something completely different. But that's 10 factorial. And so these you should do with your calculator because the numbers are going to be huge. All right, so for a problem like number 20, try to do these problems all of, well, you won't be able to do them all, but try to do as much of them that you can without using the factorial key on your calculator. So in a problem like number 14, for example, and you might even see today a permutation where when you evaluate the permutation, it looks like this, 20 factorial divided by 18 factorial. So 20 times 19 times 18 times 17 times 16 ... 3, 2, 1 on the top, 20 factorial. So there's one additional step from the problems like you did above. And then 18, 17, 16 ... 3, 2, 1 on the bottom. 18 factorial on the bottom, 20 factorial on the top. So then you'll be able to cancel all the factors from 18 factorial on both the top and the bottom. So you're left only with 20 times 19. And that's 380. Yeah, 10 factorial, it doesn't take long for these numbers to get very big very quickly. So 10 factorial, you're already up at 3 million, over 3 million. 20 times 6, 120. 9 factorial just gets rid of the 10. So 3, 6, 2, 8, 80. 9 factorial. And then if you have 10 factorial, all you would have to do to 10 times 9 factorial. So all you have to do to 9 factorial, this number, is to multiply it by 10 to get 10 factorial. I think that's what they were saying up here, that 10 factorial is equal to 10 times 9 factorial. 20 factorial is equal to 20 times 19 factorial is equal to 20 times 19 times 18 factorial. So you can use these patterns to help you simplify expressions. Now these here will be ones that you'll see when you're evaluating a permutation or a combination if you use the formula. So go ahead and evaluate these guys. How about number 16? If you have 10 students in the room and you want to select 5 of them to work in a group, how many ways can you do that? That's the question we're going to ask today. How many ways? Count the number of ways. And the answer to that question, if you had 10 students to create a group of 5 students, this would be the number of ways to do that, this expression. And while you're doing it by hand, I will do it by calculator. It's actually more tedious to do it by calculator than it is just to do it by hand. I simplified the 10 minus 5 in the denominator. 10 factorial over 5 factorial, 5 factorial. And no, it's not equal to 1. It's actually equal to a fairly large number. Well, not too large, 252. So why 252? Well, you have 10 factorial all over 5 factorial, 5 factorial. They're small enough that you could actually write them all down. That's what you have on the top. And then 5 times 4 times 3 times 2 times 1. And then another 5 times 4 times 3 times 2 times 1. And then, so if you cancel the factors, cancel identical factors, 5 times 2 is 10. And I guess we can cancel that. I think we've done this one before. Up above, it looks like a lot of similar things. 2 there and 2 there. So if you were to take 9 times 2 times 7 times 2, you would indeed get the 252. All right, then they ask you to do a couple where you're generalizing. All right, so let me do one here and see if you can figure out how to do the next one. This one here, we start with n plus 1, and then we multiply it by itself, by all of the whole numbers going all the way down to 1. So the whole number, the first whole number that's less than n plus 1, we would subtract 1 from it, and we would just get n. The next number that we would need to multiply by would be 1 less than the n. We write that, n minus 1. The next number that we would need to multiply by is n minus 1 minus another 1. Well, we say that, n minus 2. And then n minus 3 and n minus 4. And where do you stop? Well, you stop once you get to 3, 2, 1. And since you don't know what n is, you just do this dot, 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 3, 2, 1. All right, so that's the top. 3 factorial is 3 times 2 times 1. And then we're going to multiply by n minus 2 factorial. So n minus 2 factorial begins with n minus 2. And then we subtract 1 from it to get n minus 3. And then we subtract another 1 to get n minus 4. And where do we stop? Well, we stop once we get all the way down to 3, 2, 1. So you'll see that you have a lot of factors in the top that match factors in the bottom of this fraction. So you can cancel all of those. So we're going to cancel everything from n minus 2 all the way down to 1. You notice the only thing that remains then would be these pieces over here. I'm not sure what form it'll take in the answer. I'm not sure if they're going to make you multiply out a cubic polynomial or not. So I would just say this is good enough. without the foiling that you'd have to do in algebra to multiply it all out. All right, go ahead and try number 30. And then we're going to get into permutations and combinations. Okay, somebody write the answer in the chat there. And you can write it as the product of polynomials, binomials, or something like that. N plus 3 factorial. Starts off with n plus 3. Then you got to multiply it by the next whole number less than n plus 3. And if you're going from one whole number to the next lowest one, you subtract 1. So if you start with n plus 3 and you want to subtract 1, that would be n plus 3 minus 1, which is n plus 2. But then you got to multiply again by the next whole number less than n plus 2. That means you have to subtract another one. So n plus 2 minus 1 would be n plus 1. N plus 1 minus 1 would be n. N minus 1 would be n minus 1. And you can go this way all day long if you like, but you don't have to. You just have to indicate a pattern and then go all the way down to 1. And on the bottom, we start with n plus 1. I'm going to put it right underneath the n plus 1 in the numerator. And then we subtract 1 from it. Oh, I see some answers in there. Yeah, those answers are good. And then n minus 1, and then so on. 3, 2, 1. So all of these will cancel with all of these, and you're just left with those two. N plus 3 times n plus 2. All right, so this is a little bit on simplifying fractions that have common factors, and particularly factorials will have lots of common factors that you can cancel out. And we do this because the permutation and combination formulas involve this. So the first thing we're going to talk about is a permutation. And the key word here is arrangement. And you have distinct objects. So this means that if you do a permutation, and you're doing a permutation of letters of the alphabet, for example, a permutation by definition means that they're all distinct. And so they're different from one another. So you cannot choose the same, say, letter twice. But a permutation is an arrangement of items from a set, objects they call it. Order is important. So order is important, and there's no repetition. If you have the letters of the alphabet and you want to permute 3 of them, then you can't use the same letter twice. That's a definition of a permutation. You can't list the exact permutations unless you use a very small set. So let's say we're going to select 2 and order them from a set of 3 letters, A, B, and C. So from 3, we want to choose 2. We want to choose 2 and then arrange them. From 3, we want to choose 2 and then arrange them. Now, with such a small set here, we can actually list all the permutations. Now, our notation is going to be this. From 3, we're going to permute 2 of them. So it's 3 permute 2. All right, I'm going to write them all down just so you can see how many there are. So we have A, B. That's one permutation, but that would be different than BA, because the order is different, and for a permutation, order matters. We have AC or CA. We have BC or BA, and that's it. There are 1, 2, 3, 4, 5, 6 permutations. So what we'd like to do is, for any permutation, like this one, we'd like to be able to evaluate it without having to list down all the permutations. So here is the formula for NPR. For n objects, you're going to select R of them, and then you're going to arrange those R objects. So order matters. The number of ways that you can do that, you're going to take the first number, n, take its factorial, and then you're going to take the n and the R, subtract them, and then take that factorial. So here is the formula that we're going to use. And you already saw that it's in the math menu, and then it's in the probability submenu, and then it's going to be option 2. And that's how it looks on the calculator. We don't have the subscripts there. All right, so let's do our example here. If we had a permutation, then where we're going to arrange two objects from 3, then we take the 3 factorial on the top, and then you take 3 minus 2 factorial on the bottom. Well, 3 factorial is 3 times 2 times 1, and 1 factorial is just 1, so you do get 6. And here we listed them all, counted them up. Permutation order matters. All right, I might as well define combination as well, since we're here. Okay, so here we're going to choose 2 objects from 3, where order does not matter. So from 3 objects, we just want to choose 2, and we don't care if we're not going to assign them a role. Order is not important here in counting up the number of ways. Now, AB is a combination up here, but it's indistinguishable from BA because both of them include A and B. So this would be one combination. AC and CA would be identical if we're just talking about combinations. If order didn't matter, they would be the same thing. And then BC and BA would be, this should be CB here. I don't know what I was writing there. But BC and CB were the same, are the same combination. So there's 1, 2, 3 combos. So we're still selecting from n distinct objects. We're selecting R objects from n distinct objects, but for a combination, order doesn't matter. So think about playing cards. When you're dealt cards, most card games, the order in which you receive the cards is not important. You just, from the 52 cards, you choose 5, or you're being dealt 5. And you can arrange those cards in your hand however you like. You don't have to play them in order. You don't have to receive them in order. You just have to have 5 cards in the end. So if order doesn't matter, then we're dealing with a combination. The symbol that we're going to use here is C, C for combination. Now this one is also on your calculator. So when we use big numbers, we're just going to go right to the calculator and use the calculator function. But it's all 3 of the functions that we use today, the permutation, the combination, and the factorial, they're all in the same place. But for this one, combination looks NCR, and it's option 3 as opposed to option 2. All right, here's the formula for a combination. And I'm going to use just a formula where we're using variables. So n choose R, a lot of times you're going to see this like this as a mathematical. So if you see it if you see these stacked on one another without the division symbol there, this means n choose R. So I just wanted to familiarize you with the math notation. For this one, we're going to take the n factorial, and then we're going to divide by the r factorial, but we're also going to divide by n minus r factorial. So we're going to divide by 2 things. And even though we're dividing by 2 things here, it turns out that every time you evaluate this fraction, you're going to get a whole number. because we're counting the number of ways. The formula itself is not difficult. It's interpreting scenarios where you actually use combinations versus permutations. Okay, so let's evaluate this one. We take the n, 3 factorial. We divide that by the 2 factorial. And then we take 3 minus 2 factorial. We divide by both of those things. So on top, we have 3 times 2 times 1. On the bottom, 2 times 1 times 1 factorial, which is just 1. So you can see here you're going to have 6 over 2, which is 3. And when we wrote these down, here you see them. 1, 2, 3. 3 combinations. So that's the formula. Now the tough part, the formulas are simple enough, but the tough part is applying these formulas. The big difference between them is that you're choosing R objects from n distinct objects, n objects that are different. You're not going to have 2 A's or 2 B's or 2 7 of spades, anything like that. You're choosing from n distinct objects, and the difference is that for permutations, you're going to arrange those objects that you choose. Whereas permutations, you're just counting the number of ways to choose so many objects from a larger group of so many objects. Perms and combos. Take a look at and evaluate some of these. Let's try to do them by hand, but just keep in mind that these are pretty trivial if you use your calculator. So I definitely would use the calculator for something like this, but maybe as we evaluate these, we'll just use the formula. So we're choosing here 10 objects from a group of 15. And how many ways can we do that? Well, we start with the big number, 15 factorial on the top, and then the little number, 10 factorial on the bottom. But then we also have 15 minus 10 factorial on the bottom. All right, 15 times 14 times 13 times 12 times 11 times, and then I'm just going to write this as 10 factorial, which would continue times 9 times 8 times 7 times 6 all the way down. And the reason I'm going to stop at 10 factorial is because I have a 10 factorial down here that I want to cancel out. But I do have the 5 factorial remaining. And 5 factorial is 5 times 4 times 3 times 2 times 1. So it's still going to be a large number, but maybe I'll do it this way. 4 times 3 is 12, so I can cancel out a 12. 5 would cancel with the 15, leaving a 3 on the top. And I still have to cancel at the 2, and there's only one even number left, so 2 cancels with the 14, leaving a factor of 7. So after all of that, just take all those numbers that remain on the top and multiply them all together. And this would be 3003. And on the calculator, we're going to take 15 and then go to the math menu and over to the probability submenu. And then there's the NCR. And 10. All right, so be able to cancel them out by hand, be able to use the calculator, both methods. So this one right here is a probability that we'll later calculate. And the probability that you'll be asked to calculate would be, what is the probability if you're dealt a 4-card hand in a standard 52-card deck in which all of the cards are red? So how many all red hands would you get from being dealt? What's the probability of getting an all red hand if you're dealt 4 cards from a 52-card deck? And if you evaluate this here, that's going to be the answer. Okay, did you get number 22? This one is the permutation, NPR. So for this one, we take 10 factorial and divide by 10 minus 7 factorial. So that's 10 factorial over 3 factorial, which is 10 times 9 times 8 times 7 times 6. You know, and sometimes if you don't trust your calculator, you might want to just write them all out like this, just to convince yourself that, yeah, it really is that large. So for this one, we're going to cancel out the 3, 2, 1, but you've got all of these 7 numbers here that we're multiplying together. And that's going to make it very large very quickly, 604,000. Or look what happens when I take 10 times 9 times 8 times 7 times 6 times 5 times 4. Okay, and if there's one thing that you do realize in this section, here's a nice little blurb. Permutations and combinations are almost identical. You're selecting from n distinct objects. You're selecting 4 items. The only difference is that in a permutation, you have to consider order. Order matters. So given this, we can say that NPR is equal to NCR. Okay, so choosing n objects from R objects, choosing n objects from R objects. But for the permutations, we have to arrange them. So if we have, say, if we're going to choose 3, we then have to consider how many arrangements there are of those 3 items, arranging all 3 of them. And so all you have to do here is to multiply by R factorial. I think this formula is better than the other one, which is this one here. NCR is equal to NPR divided by R factorial. These two algebraically are the same. And you can use the formula for NPR and NCR to confirm this. But this one might be helpful to you. Select the objects first, and then at the end, arrange them. Arrange all of them. All right, I don't have instructions on these, but okay. Permutation, combination, or neither. Not everything's going to be a permutation or a combination. If you were going to count the number of ways to do something, in this case, the university president is going to select 2 of the vice presidents to attend a ceremony. Would a permutation be involved, or a combination, or neither? Now, a couple of ways that you can choose the neither. If there's a scenario where you can choose the same thing twice, repetition is permitted. Repetition is not permitted for permutations and combinations. That is, you can't choose the same object twice and count it again. So, repeats, permitted. And for permutations and combinations, repetition is not allowed. So that would be one way that you can determine, you know, if you're dealing with a permutation or a combination. Now, once you've decided that repetition is not permitted and you have n distinct objects you are selecting from, right? Got to select from n distinct objects. You got to select R objects, and you can't have any repeating. Then, if order matters, then you go from combination to permutation. Okay. University president selects 2 of her vice presidents to attend the ceremony. So of all the vice presidents that are out there, they're all distinct individuals. So distinct individuals, there are no clones of these vice presidents. They're all different. Then she's going to select 2 of them. Now, she can't select the same vice president twice, because then she would have just a single person going to this award ceremony. So repetition is not permitted. So now you're down to permutations and combinations. Now, let's imagine that we have these 2 individuals that we've selected. Does order matter in this situation? No, order does not matter. So this is a combination. Order would matter if not only the president was going to select the two vice presidents, but was going to assign the first one as being the parliamentarian and the second one to be a just regular member. Then you have two arrangements. Arrangements matter. What about 34? Student bought 4 books. Christmas time example. One for his father, one for his mother, one for his younger sister, and one for his older brother. Think about all the possible books that are out there. Well, let's say that there's 1,000 books at the bookstore or at Barnes and Noble that are different from one another. Are they different from one another? Is repetition allowed? That is, could the student buy the same book for the father and the sister? Yeah. So because repetition is permitted here, we have to say it is neither a permutation or combination. Okay. All right, let's just take a look at a couple of these. I'm not going to evaluate them. I'm just because the evaluation part is just kind of something that you can just throw on afterwards by using your calculator. But by the way, if you've done this one is meets at the home of one of its 10 members. In December, the club selects a host for each meeting of the next year. All right, so there are 10 members. And in this case, order matters because, you know, we're selecting members to host a meeting. And it's different than if I host the January meeting versus I host the April meeting. Those are two different schedules of how you could arrange the host for next year. So order matters, so this is a permutation. And we don't want, you know, we have just the 10 individual members, and we're not going to select one member to host twice. So repetitions are not permitted. We're selecting from the homes of the 10 individuals, they're all distinct, but order matters when we're establishing a schedule. All right, the rest of these are all where we're going to be using permutations and combinations and the multiplication method. So we'll try to do a couple of examples here. All right, in a long distance foot race, how many different finishes of the first place for the first places are possible if 50 people are running? So we have N is equal to 50. We have 50 people running in the race. These are all distinct individuals. Again, we don't have clones running out there, right? Now, from those, we're going to select 5 to finish in first, second, third, fourth, and fifth place. In a race like this, can we just select the 5 top finishers and say we're good? Or do we need to arrange them? In this context, does order matter? That's the question you have to ask. Does order matter here in a race? Or is it just good if you finish in the top 5? Yeah. Order matters. So we have a permutation. All right. So we have from 50, we're going to choose 5, excuse me. And you can evaluate this with your calculator, but it's, you know, close to 250 million possibilities just with 5 finishers. But we have 50, right? So 50 times 49 times 48. So you can do this one with the multiplication principle. You have 50 runners. How many different runners can come in first? 50. Once that person, we've identified that person who comes in first place, how many different ways can someone come in second place? Well, there are 49 racers. We need to select 1. And after the first 2 finish, there are 48 runners that we could possibly put in third place, 47 in second place, and 46. So we can actually use the multiplication rule here. And it turns out that if you evaluate these in both ways, you'll get the same number. So sometimes there's more than one way to count the number of permutations. Next one, 9 cards. So we're eventually going to build up to the 52 cards. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So from those 9, we're going to choose some. A 3-card hand is dealt. So we're going to choose 3. 1, 2, 3. How many hands are possible? In which? Okay, if order is taken into consideration, that's a definition of a permutation. Most of the time when you're playing cards, order doesn't matter. You just kind of get a bunch of cards and you put them in your hand, and you don't have to play them in a certain order. You don't have to arrange them in a certain order. When order is not taken into consideration, you have a combination. So pick out the N, pick out the R, decide if order matters, decide if these other criteria are occurring, that is, repetition is not allowed. And so this one would be 9P3, and this one would be 9C. This one is 504, and this one is 84. And just to illustrate that relationship we had before, NPR is equal to NCR times R factorial. So if you took 504, if you notice that that's 84 times the smaller number R is 3 times 3 factorial, which is 6. So 6 times 84 would be 94. So this one would say, choose the number of, determine the number of ways you can choose 3 cards, and then multiply it by 3 factorial, because that's the number of ways that you can arrange those 3 cards. From 3, arrange all 3.